Hi all. ഇന്ന് നമ്മൾ ലാസ്റ്റ് തിയറമാണ് ഈ മൊഡ്യൂളിൽ ഡിസ്കസ് ചെയ്യുന്നത്. തിയറം 7.8. ഈ തിയറത്തിൽ പറഞ്ഞിരിക്കുന്നത് ദാറ്റ് ഈസ് ദ എക്സിസ്റ്റൻസ് ഓഫ് ദ റിയൽ കണ്ടിന്യൂസ് ഫംഗ്ഷൻ. That means continuous everywhere on the real line, which is nowhere differentiable. Okay, so this theorem establishes the existence of such a function. കോംപ്ലക്സ് അനാലിസിസ് ഡിസ്കസ് ചെയ്യുകയാണെങ്കിൽ അത് വളരെ ഈസി ആയിട്ട് നമുക്ക് ഇത്തരം ഫംഗ്ഷൻസ് അവിടെ കണ്ടെത്താൻ പറ്റും. വളരെ എളുപ്പത്തിൽ പറയാൻ പറ്റുന്ന ഒരു ഫംഗ്ഷൻ എഫ് ഓഫ് ഇസഡ് ഈക്വൽ ടു ഇസഡ് കോൺജുഗേറ്റ് ആണ്. നമുക്കറിയാം ഇസഡ് കോൺജുഗേറ്റ് എന്നുള്ള ഫംഗ്ഷൻ എക്സ് പ്ലസ് ഐ വൈ എന്നാണ് വിളിക്കുക. ഇതിൽ സി ആർ ഇക്വേഷൻസ് നിങ്ങൾ പഠിച്ചിട്ടുണ്ടാകും. യു എക്സ് യു വൈ വി എക്സ് വി വൈ. ഇതുപയോഗിച്ച് നമുക്ക് വളരെ ഈസി ആയിട്ട് ഈ ഫംഗ്ഷൻ ഒരു സ്ഥലത്തും ഡിഫറൻഷ്യബിൾ അല്ല എന്ന് പ്രൂവ് ചെയ്യാൻ പറ്റും വളരെ ഈസി ആയിട്ട്. ഇതിൻ്റെ കമ്പോണൻസ് നോക്കിക്കഴിഞ്ഞാൽ യുവും വിയും ഇവിടെ കണ്ടിന്യൂസ് ഫംഗ്ഷൻസ് ആണ്, പോളിനോമിയൽസ് ആണ്. അതുകൊണ്ട് ഈ ഫംഗ്ഷൻ എല്ലാവരും കോംപ്ലക്സ് പ്ലെയിനിൽ മുഴുവൻ കണ്ടിന്യൂസ് ആയിരിക്കും. വളരെ ഈസിയാണ് നമുക്ക് ഇത്തരം എക്സാമ്പിൾസ് കോംപ്ലക്സ് അനാലിസിസ് അല്ലെങ്കിൽ R2 എന്ന് പറയുന്ന സിറ്റുവേഷനിലൊക്കെ കണ്ടെത്തുക എന്നുള്ളത്. അതേസമയം ഇത്തരം ഫംഗ്ഷൻസ് റിയൽ അനാലിസിസിൽ അത്ര ഈസി ആയിട്ട് കണ്ടുപിടിക്കാൻ പറ്റില്ല. ഇത് എവ്രിവെയർ കണ്ടിന്യൂസ് ആൻഡ് നോവർ ഡിഫറൻഷ്യബിൾ. അത്തരമൊരു ഫംഗ്ഷൻ്റെ എക്സിസ്റ്റൻസ് ആണ് ഈ തിയറത്തിൽ പറയുന്നത്. അതിന് നമ്മൾ കൺസിഡർ ചെയ്യുന്ന അതിലേക്ക് എത്തുന്നതിന് മുന്നേ, ആ ഫംഗ്ഷനിലേക്ക് എത്തുന്നതിന് മുന്നേ നമ്മൾ ഇത് കൺസ്ട്രക്ട് ചെയ്തെടുക്കാൻ കഴിയുന്നത്. അതുകൊണ്ടാണ് ഇത് തിയറായിട്ട് നമ്മൾ ടെക്സ്റ്റിൽ ഡിസ്കസ് ചെയ്തിരിക്കുന്നത്. ഇത് നമ്മൾ ഇപ്പോൾ നമ്മുടെ എഫ് ഓഫ് എക്സിലേക്ക് എത്തുന്നതിന് മുന്നേ, നമ്മുടെ റിക്വയർഡ് ഫംഗ്ഷനിലേക്ക് എത്തുന്നതിന് മുന്നേ നമ്മളൊരു കൺസ്ട്രക്ഷൻ നടത്താൻ പോവുകയാണ്. കൺസ്ട്രക്ഷൻ നടത്തുന്നത് എങ്ങനെയാണ്? ലെറ്റ് മീ കൺസിഡർ a famous function called phi of x equal to mod x. വളരെ ഇൻട്രസ്റ്റിംഗ് ആയിട്ടുള്ളൊരു ഫംഗ്ഷനാണ്. -1 എന്ന് പറയുന്ന ഇൻ്റർവെല്ലിൽ ഈ ഫംഗ്ഷൻ നമ്മൾ കൺസിഡർ ചെയ്യും. നമുക്ക് എല്ലാവർക്കും അറിയാം -1 to 1 എന്ന് പറഞ്ഞ ഇൻ്റർവെല്ലിൽ ഈ ഫംഗ്ഷൻ എന്ന് പറയുന്നതിൻ്റെ ഗ്രാഫ് ഇങ്ങനെയായിരിക്കും. ഈ പറഞ്ഞ ഫംഗ്ഷൻ്റെ പ്രത്യേകത ഇതൊരു കണ്ടിന്യൂസ് ഫംഗ്ഷൻ ആയിരിക്കും. ഈ ഇൻ്റർവെല്ലിൽ എടുത്തു കഴിഞ്ഞാൽ ഇവിടെ ഈ ഫംഗ്ഷൻ ഒരു കണ്ടിന്യൂസ് ഫംഗ്ഷൻ ആയിരിക്കും. ഓക്കെ, ഇതാണ് ഇതിൻ്റെ ഒരു ആദ്യത്തെ പ്രത്യേകത. സോ ഈ പറഞ്ഞ ഫംഗ്ഷൻ വേറൊക്കെ പ്രത്യേകത എന്തൊക്കെയുള്ളതെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഫൈ ഓഫ് എക്സ്, ഫൈ ഓഫ് വൈ. ഓക്കെ, ഫൈ ഓഫ് എക്സും ഫൈ ഓഫ് വൈയും ഒബ്സർവ് ചെയ്ത് കഴിഞ്ഞാൽ, അതായത് മോഡുലസ് ഓഫ് മോഡ് എക്സ് മൈനസ് മോഡ് വൈ, ഈ പറയുന്നത് എല്ലായ്പ്പോഴും ലെസ് ദാൻ ഓർ ഈക്വൽ ടു മോഡ് എക്സ് മൈനസ് വൈ ആയിരിക്കും. ഇത് മോഡുലസിൻ്റെ പ്രോപ്പർട്ടിയാണ്. ഇത് വളരെ ഈസി ആയിട്ട് നമുക്ക് പ്രൂവ് ചെയ്യാം. ട്രയാങ്കിൾ ഇൻഇക്വാലിറ്റിയുടെ കോൺസിക്വൻസ് ആയിട്ട് വരുന്നതാണ്. സോ അറിയാത്തവരുണ്ടെങ്കിൽ I will give it as an exercise. Prove that this inequality. Okay, prove this inequality. ഇനി ഈ പറഞ്ഞ ഫംഗ്ഷൻ്റെ അടുത്തൊരു പ്രത്യേകത എന്ന് പറയുന്നത്, അതായത് മോഡ് ഫൈ ഓഫ് എക്സ് മൈനസ് ഫൈ ഓഫ് ഐ ലെസ് ദാൻ ഓർ ഈക്വൽ ടു മോഡ് എക്സ് മൈനസ് വൈ ആണ്. ഇവിടെയുള്ള ഏത് എക്സും വൈ എടുത്തു കഴിഞ്ഞാലും ഇതിൻ്റെ മീനിങ് എത്രയേ ഉള്ളൂ. ഇവിടെയുള്ള ഏത് എക്സ് കോമ വൈ നിങ്ങൾ ചൂസ് ചെയ്ത് കഴിഞ്ഞാലും മോഡ് എക്സ് എന്ന് പറയുന്നത് ഈ ക്വാണ്ടിറ്റി ആയിരിക്കും, മോഡ് വൈ എന്ന് പറയുന്നത് ഈ ക്വാണ്ടിറ്റി ആയിരിക്കും. ഇപ്പോൾ ഇമേജസ് തമ്മിലുള്ള ഡിഫറൻസ് ദാറ്റ് ഈസ് ഓൾവേസ് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു ഇമേജസ് തമ്മിലുള്ള ഡിസ്റ്റൻസ് എന്ന് പറഞ്ഞാൽ ഇതാണ് ഇവിടെ. ദാറ്റ് ഈസ് ഓൾവേസ് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു ദ ഡിസ്റ്റൻസ് ബിറ്റ്വീൻ ദി കറസ്പോണ്ടിങ് പോയിന്റ്സ്. ഓക്കെ, ഇതാണ് ഇവിടുത്തെ ഒരു ഐഡിയ. ഇനി അതേസമയം നിങ്ങൾ if you consider 2 points x comma y for which there is no integer in between these two x and y. എന്നുവെച്ചാൽ ഇവിടെ ഇൻഡിജേഴ്സ് എന്ന് പറയുന്നത് ഇത് 0, ഇത് 1, ഇത് -1. ദീസ് ആർ ദി 3 ഇൻഡിജേഴ്സ്. നിങ്ങൾ എക്സ് ആൻഡ് വൈ ചൂസ് ചെയ്യുന്നത് ഇൻ ബിറ്റ്വീൻ 2 ഇൻഡിജേഴ്സ് ആണെങ്കിൽ ഈ പറയുന്ന മോഡുലസ് ഓഫ് മോഡ് എക്സ് മൈനസ് മോഡ് വൈ എന്ന് പറയുന്നതിൻ്റെ മോഡുലസ് ഇമേജിൻ്റെ ഡിസ്റ്റൻസ് ദാറ്റ് വിൽ ബി സെയിം ആസ് മോഡ് എക്സ് മൈനസ് വൈ. ഓക്കെ, കാരണം ഇൻഡിജേഴ്സ് ഇതിന് ഇൻ ബിറ്റ്വീൻ ഇല്ലെങ്കിൽ ഈ പറയുന്ന ഫംഗ്ഷൻ്റെ പ്രത്യേകത ഈ പറയുന്നത് ഇമേജ് തമ്മിലുള്ള ഡിസ്റ്റൻസും പിന്നെ എന്താ പറയുക പോയിന്റ്സ് തമ്മിലുള്ള ഡിസ്റ്റൻസ് സെയിം ആയിരിക്കും. കാരണം ഇത് ഫംഗ്ഷൻ എന്ന് പറയുന്നത് ഒന്നല്ലെങ്കിൽ വൈ ഈക്വൽ ടു എക്സ് എന്നോ അല്ലെങ്കിൽ വൈ ഈക്വൽ ടു മൈനസ് എക്സ് എന്നുമാണ്. അപ്പോൾ അതുകൊണ്ട് തന്നെ ഡിസ്റ്റൻസുകൾ എടുക്കുമ്പോൾ രണ്ടും സെയിം ആയിരിക്കും. ഇത്രയൊക്കെയാണ് ഈ പറഞ്ഞ ഫംഗ്ഷൻ്റെ പ്രോപ്പർട്ടി. ഈ പറഞ്ഞ പ്രോപ്പർട്ടി ഉപയോഗിച്ച് നമ്മൾ വിൽ കൺസിഡർ എ ന്യൂ ഫംഗ്ഷൻ ഫൈ, or we consider the extension of this function. We extend this with period 2. Okay, so for all x belongs to real numbers. So this function is defined only on or -1 to 1. Okay, Now we define the new function throughout the real line. Okay, how will you define this function? We define this function by extending our our mod x to all of these real numbers. Okay, all of this real line. I'll make this is the this is our function. We extend this with these properties. Okay, we extend with the property that phi of x plus 2 equal to phi of x. That means the period of this function is 2. Okay, like this. So what we expected is the properties of this function in between minus and 1 will be obtained throughout this real number. Okay, because we are considering the same function over 1 to 3. Okay, 1 to 3 we have the same function, and again 3 to 5 we have the same function, and minus this point is minus 2, so minus 1 to minus 3 we have the same function. Okay, that means this property holds for every x and y. If we choose any x here and any y here, so this is our x and this is y, then we can get with the property that if this is x and that is y, then this is our phi of x. Okay, and if you consider this, then this is our phi of y. This is our phi of y, and this is our phi of x. That means if you consider any x and y anywhere from this real line, then phi of x and phi of y will take the same value that obtains at some point. Suppose this is x prime and this is our y prime. Okay, x and y in real line you can get 2 points x prime and y prime such that phi of x prime is same as phi of x, phi of y prime is same as phi of y. X prime y prime minus 1 to 1 അകത്ത് വരുന്ന തരത്തിലുള്ള രണ്ട് എക്സ് പ്രൈമും വൈ പ്രൈമും നമുക്ക് കണ്ടെത്താൻ പറ്റും. അതുകൊണ്ട് തന്നെ ഇതിനകത്ത് എന്തൊക്കെ പ്രോപ്പർട്ടി ഉണ്ട് ആ പ്രോപ്പർട്ടി എല്ലാം നമുക്ക് ത്രൂ ഔട്ട് ഈ പറയുന്ന റിയൽ ലൈനിൽ മുഴുവൻ കിട്ടും എന്നുള്ളതാണ് ഇതിൻ്റെ ഈ എക്സ്റ്റൻഷൻ. അല്ലെങ്കിൽ ഇതിനെ നമ്മൾ പീരിയോഡിക് ആയിട്ട് എക്സ്റ്റെൻഡ് ചെയ്താൽ ഈ പറഞ്ഞ ഫംഗ്ഷൻ ഈ പ്രോപ്പർട്ടി ഉണ്ടാവും എന്നുള്ളതാണ് എൻ്റെ പ്രത്യേകത. ഓക്കെ, സോ ദിസ് ഈസ് അവർ ഇൻഫാക്ട് ദിസ് ഇസ് നോട്ട് ഫൈ ഓഫ് എക്സ്. ഫൈ ഓഫ് എക്സ് ഇസ് ദിസ് ഫംഗ്ഷൻ. ഓക്കെ, അല്ലെങ്കിൽ ഫൈ ഓഫ് എക്സ് ഇങ്ങനെ ഡിഫൈൻ ചെയ്ത് നമ്മൾ എക്സ്റ്റെൻഡ് ചെയ്തു ത്രൂ ഔട്ട്. സോ ഫൈ ടേക്സ് ദിസ് ഫോം. സോ ദിസ് ഇസ് ദ ഗ്രാഫ് ഓഫ് ഫൈ ഓഫ് എക്സ്. Okay, using this phi we will construct our required function f of x. Okay, which is everywhere continuous and nowhere differentiable. Okay, so the first idea is to define f of x. F of x is a series from n equal to 0 to infinity. It's an infinite series. 3 by 4 to the power n times phi of 4 raised to n x. Okay, so this is our function f of x for every x belongs to R. Okay, we know that this value is 1. So if you consider this phi, then phi of x, mod phi of x is always less than or equal to 1, because the maximum possible value of this phi of x is 1, because we set the maximum possible value of this phi of x is 1. Now if we consider this f of x, now we consider this series first. You can observe this series. If we consider this as our modulus of this value, 3 by 4 raised to n phi of 4 raised to n x can be made less than 3 by 4 raised to n, because the maximum possible value of this quantity is 1. So this upper bound of this is, if we take this as some fn of x, then mod fn of x is always less than or equal to some mn. Okay, but we know that summation mn, that is summation 3 by 4 raised to n, is convergent, because this is a infinite GP. Okay, from n equal to 0 to infinity, therefore this GP converges because the common ratio is less than 1. So we can say that sigma mn is convergent, sigma from n equal to 0 to infinity. Therefore, sigma fnx is convergent. Fnx is uniformly convergent. Okay, this is theorem discussed in earlier classes, which is also called the Weierstrass test. Okay, so this using this test, what we have discussed immediately after the characterization of uniform convergence, we can say that this f of x, or right hand side, converges uniformly. Okay, converges uniformly. Since this converges uniformly, this converges to a continuous function, because the sequence of partial sums of this right hand side is always continuous, because phi is continuous, 3 by 4 raised to n is continuous. Then all these fn of x, if we consider this as fn of x, these fn of x are all continuous. Therefore, the sequence of partial sums are also continuous. Okay, so sequence of partial sums, that is a sequence of continuous functions which converges uniformly converges to some function, then which is also continuous. So this f of x is being the limit of uniform limit of the sequence of continuous functions. F of x is continuous everywhere. Continuous everywhere. Okay. So first, so this is going to be our candidate. F of x is continuous. Next, we will prove that this f of x is not differentiable at any point of real, any point, any real number x. Okay, so let us fix x belongs to R, and we'll prove that if we fix any x, then we can prove that this f of x is not differentiable at x. Okay, so the derivative of derivative of this f at x is defined to be limit h tends to 0, f of x plus h minus f of x divided by h. That means in order to get the differentiability, we this limit should exist. Okay, so that means limit h tends to 0, f of x plus h minus f of x divided by h exists. Okay, we will prove that this limit does not exist. Okay, that means we can find a certain quantity, say delta n, or we will find out some sequence of numbers, say delta n, which converges to 0, but f of x plus delta n minus f of x divided by delta n does not tends to or tends to infinity. Okay, so to prove this is not this limit does not exist, we will find out a certain sequence delta n which converges to 0, and we have this quotient difference converges to diverges to infinity, which shows that this limit does not exist. If it would exist, if this limit were exist, then we can expect this also converges to some finite quantity. Okay, so this is the idea what we have idea used to prove this f dash x the non-existence of this f dash x. Okay, so first we set our intention is to find out some sequence delta n or delta m which tends to 0, but the divide quotient difference does not tend to a finite quantity or a fixed real number, which but this goes to infinity. Okay, so that we choose delta m is equal to plus or minus half of this 4 raised to minus m. This is our delta m. Okay, and this the signs of this delta m are to be chosen in such a way that there is no integer in between 4 raised to mx and the number 4 raised to mx plus delta m. Okay, so that means what is this number? This number is nothing but 4 raised to mx plus 4 raised to m into delta m. What is this number? this number is 4 raised to mx. This delta m is to be chosen in such a way that this is plus or minus 4 raised to m into 1 by 2 4 raised to minus m. Okay, so this is going to be 4 raised to mx plus or minus half. Okay, so this is our by cancelling these two you can get this is 4 raised to mx plus or minus half. Okay, so this is 4 raised to mx and this is 4 raised to mx and this is 4 raised to m plus or minus 4 raised to mx plus or minus half. Okay, then you can easily choose this sign plus or minus as first you consider 4 raised to mx, then consider 4 raised to m plus x, 4 raised to mx plus half and 4 raised to mx minus half. Okay, so this this number is chosen as 4 raised to m plus 4 raised to mx plus half. Okay, so you need to choose delta m as either of this number either of plus half 4 raised to minus m and minus half 4 raised to minus m in such a way that there should be no integer in between them. If there is no integer in between these two numbers, then we have to choose this delta m as minus half. Okay, 4 raised to minus half times 4 raised to minus m. If there is no integer in between these two numbers 4 raised to mx and 4 raised to mx plus half, then we can choose delta m as plus half 4 raised to minus m. Okay, this is the way we choose the sign of this delta m. Okay, these are going to be the sequence or candidate to prove this derivative does not exist. Okay, so after that then this can be that means this selection can be done because of these reasons. Okay, that means the modulus of that 4 raised to m into delta m is nothing but half. Okay, that means this number, the modulus of this number is always half. That means when you move beyond this or backward to this 4 raised to mx minus half, then or 4 raised to mx plus half, you can get you can easily choose one of these values satisfying the condition that 4 raised to mx 4 raised to there is no integer between in between 4 raised to mx and 4 raised to mx plus delta m. Okay, so the sign is chosen in such a way that there is no integer in between these two numbers. So that is the idea here. Now we'll show that that limit does not exist. For that we define gamma n. What is gamma n? Gamma n is phi of that 4 raised to n into x plus this is delta m, not delta n, this is delta m itself, minus phi of 4 raised to nx, okay, divided by this delta m. This is our gamma n. We have chosen gamma n in this manner. Okay, what is gamma n? Gamma n is obtained by taking difference between these two numbers, okay, divided by delta m. Now you consider the modulus of gamma n. Okay, when we have three cases when this n is greater than m, n is greater than n is greater than m, we have these two numbers 4 raised to n x plus delta m. Just observe these two numbers 4 raised to n into x. If n is greater than m, you can simplify these these brackets. That will be 4 raised to n x plus this will be 4 raised to n into plus or minus half 4 raised to minus m. Okay, and this number is 4 raised to nx. Now we have 4 raised to nx plus by multiplying this you can get plus or minus half times 4 raised to this number is n minus m. Okay, then this is 4 raised to nx. Now you observe this. Okay, when this case happens, n is greater than m, this number is greater than this number. Okay, that means n minus m is always greater than 0. That means this will be at least 1. Okay, then this whole quantity is plus or minus, this whole quantity is some 2k. This is at least 1 means you can cancel 1 2 from this, and the remaining will be an even number. So this is like 4 raised to nx plus or minus 2k and 4 raised to nx. That is the behavior of these 2 points. Okay, so when you observe this phi of 4 raised to nx plus or minus 2k and phi of 4 raised to nx, then we can say that this number can be obtained by adding 2 or multiple of 2 to this number. Then the phi value will be the same, because our assumption is phi of x plus 2 is equal to phi of x for every x. So this, if this is 2, then we can say that phi of 2 into 2, that is when you apply this 2 times, you can get phi of 4 x plus 4 is equal to phi of x. And if you can replace any 2k with this part, okay, that means phi of this value and phi of this value will be the same. Okay, because this n is greater than m. In that case, we have gamma n is always 0. Okay, when you consider gamma 1, gamma 2, gamma 3, etc., up to this m, we can expect this gamma n will be 0. Okay, the other case is 0 less than or equal to n less than m. Okay, so this is up to this m. What happened to this all the way up to this m? Okay, this is less than or equal to m. Okay, in that case we can get that modulus of gamma n is always less than, or what is modulus of gamma n? Modulus of gamma n is this, that is phi of 4 raised to n x plus delta m minus phi of 4 raised to n x, okay, divided by delta m. Okay, that is equal to this can be written as this is less than or equal to 4 raised to n x plus delta m minus 4 this is 4 raised to nx divided by delta m, because we know that modulus of phi of x minus phi of y is less than or equal to modulus of x minus y. Okay, that can applying that result, you can get this difference is always less than or equal to these two difference. Okay, then you can cancel this 4 raised to nx from both sides. We can get this is equal to delta m 4 raised to n divided by delta m, which is equal to 4 raised to n. That means in this case we have mod gamma n is always less than or equal to 4 raised to n. Okay, so these are the properties. Once you define this gamma n, then these are the properties. Up to this m, we have modulus gamma n is less than or equal to 4 raised to n, and after that, that gamma n is always 0. Okay, and we have what is mod gamma n. What is mod gamma m? Okay, mod gamma m in particular, we know that this also mod gamma n is always less than or equal to 4 raised to n, but when you observe this mod gamma m, you can get that is because of this phi of 4 raised to m, we are writing gamma m, so x plus delta m phi of 4 raised to mx divided by delta m. Okay, so in this case we can say that there is no we have chosen delta m in such a way that there is no integer in between this and this number. Okay, therefore there is no integer between this. If we take this as some s and this is t, then there is no integer between s and t. Then the distance between phi of this, phi of s and phi of t is same as distance between s and t. Okay, so this here we can get the equality. Okay, equality that 4 raised to m into x plus delta m minus 4 raised to m into x. Okay, so that distance will be the same. because there is no integer in between these two quantities. So this is going to be 4 raised to n. Okay, so if you write all this, even you can get this mod gamma n is less than or equal to 4 raised to n. More precisely, at the point m, or at gamma m, we have the modulus is exactly same as here. There is no inequality. Here we have equality, that is same as 4 raised to n. Okay, now we consider the divide quotient, that is f of x plus h minus f of x divided by h. Okay, for this h we substitute that quantity delta m, then we can get modulus of f of x plus delta m minus f of x divided by instead of h we substitute delta m. We know that this delta m tends to 0, okay, because of the definition. The definition of delta m is nothing but this one. As m tends to infinity, we can say that delta m, that is 4 raised to minus m, that goes to 0. So we know that delta m tends to 0 as m tends to infinity. But we know that we will prove that this tends to infinity as m tends to, or as delta m tends to 0. So from that you can conclude f dash x does not exist. Okay, for that we simplify this. What is f of x plus delta m minus f of x divided by this quantity? Okay, so that is by definition of f of x, we have this is modulus of summation n equal to 0 to infinity. This is 3 by 4 raised to n, phi of 4 raised to n. This is instead of x we have this number, x plus delta m. This is the definition of the f of x, and f of x plus delta m. Then here we have delta f of x, that is n equal to 0 to infinity, 3 by 4 raised to n, phi of 4 raised to n plus 4 raised to m times x. There is no delta, so this is x. Okay, divided by we have delta m. So by simplifying this, you can get this will be summation n equal to 0 to infinity. By grouping this, you can get this is 3 by 4 raised to n, and this will be phi of 4 raised to n x plus delta m minus this one, that can be replaced by some gamma n divided by delta m. Okay, so this is from this you can write this is 3 by 4 raised to gamma n, because the when you take this out, then the remaining quantity is defined as gamma n. Okay, now you consider this is the modulus. Now we have we know that from this can be written as summation n equal to 0 to m, 0 to m, this 3 by 4 raised to n gamma n plus summation n equal to m plus 1 to infinity 3 by 4 raised to n gamma n. Okay, but we know that gamma n is equal to 0 for n is greater than this n is greater than m. Okay, so this can be considered as 0. Then the remaining will be this is equal to summation n equal to 0 to m, this quantity 3 by 4 raised to n gamma n. Okay, so this is the case. Now we split this as this is equal to summation n equal to 0 to m minus 1 3 by 4 gamma n 3 by 4 raised to n gamma n plus this 3 by 4 raised to m gamma m. Okay, but this we know that mod gamma m is nothing but that same as this 4 raised to m. Okay, and this is greater than or equal to modulus of 3 by 4 raised to m gamma m minus the remaining. Okay, by applying triangle inequality in like this: mod a minus or mod a plus b is greater than or equal to mod a minus mod b. Okay, by applying this you can get this minus this summation n equal to 0 to m minus 1 3 by 4 raised to 3 by 4 raised to n mod gamma n. Okay, then this becomes 3 by 4 raised to first of all we can simplify this one, then that will be 3 raised to m divided by 4 raised to m into mod gamma m, but mod gamma m is equal to 4 raised to m, so this will be 3 raised to m. Okay, so 3 raised to m minus, and here we have we know that mod gamma n is always we have already proved that in that case mod gamma n is always less than or equal to 4 raised to n. So minus mod gamma n is always greater than or equal to minus 4 raised to n. So we can replace this minus mod gamma n can be replaced by corresponding number plus or we can write that is minus of this can be written as we write first it as plus summation n equal to 0 to m minus 1 3 by first if we replace this by plus times that we write m minus 1 here, and this we write minus mod gamma n. We know that minus mod gamma n can be replaced by this is 3 by 4 raised to n is there, and this bracket can be replaced by minus 4 raised to n. So this becomes 3 raised to m plus summation n equal to 0 to m minus 1 3 raised to n divided by 4 raised to n into this can be replaced by minus times 4 raised to n. Now you can cancel these two. Okay, so that the remaining will be 3 raised to m minus summation n equal to 0 to m minus 1 3 raised to n again. Okay, so this is a GP. Okay, this start from 1 plus 3 square plus all the way up to, so this is like 1 plus 3 square plus etc plus 3 raised to m minus 1. Okay, all the way up to n minus 3 power of m minus 1. So what is the sum of these terms? Okay, so the a into this r minus this is r is 3 here, r raised to here we have m numbers, so we have 3 raised to m minus 1 divided by 3 minus 1. So this a is 1 here, so 1 into 3 raised to m minus 1 divided by 3 minus 1. So this is the sum of these terms. So that becomes this can be written as 3 raised to m, and this sum is minus of we have 3 raised to m minus 1 divided by 2. Okay, so this is the value of this bracket. So that will be 2 raised to m 2 times 3 raised to m minus, by taking the LCM, 3 raised to m plus 1 divided by 2. So this will be 3 raised to m this is 2 times 3 raised to m minus 3 raised to m, that is 3 raised to m itself plus 1 divided by 2. Okay, so this is the value of the left hand side. What is left hand side? Left hand side is f of x plus delta m minus f of x divided by delta m, that is left hand side. So we can say that this is always greater than or equal to this number. Okay, so as m tends to infinity, we know that right hand side tends to infinity, so implies this tends to infinity. Okay, f of x plus delta m minus f of x divided by delta m tends to infinity. Okay, so this m tends to infinity means delta m tends to 0. That means delta m tends to 0, we have this quotient difference tends to infinity, which shows that f dash of x does not exist. Okay, so this proves the non-differentiability of f. Okay, this proves the existence of everywhere continuous and nowhere differentiable function. Okay, with this we can conclude the module 3. In the next class onwards we will discuss module 4, that is the last module of our syllabus. Okay, thank you.